Hi class, today we're going to be talking about truth trees. Again, truth trees are important because there are steps along the way. We're going to take language like a paragraph argument. We're going to break that down into symbols. We're then going to take the symbols that we have, create a truth tree, and from that we can see whether the argument is logically valid or not. Again, the truth of the premises are different, question, but we can see whether it's in the right logical structure using truth trees, right? So the first step is taking language and turning it into symbols. Now we've done this a little bit already. I want to review that. I want to look at symbols and turn it into language so we can go both directions. And then I want to take some symbols and an argument and create truth trees and show you sort of how that's going to work, right? So I'm going to share my screen. All right. So on the left over here where the cursor is, you can see language, right? So there's a key up here. Logic is easy. We're going to make P, right? Because every going to need its own letter. Logic is fun. We're going to make Q. And then symbols can be used. We're going to make R. Okay? So number one says logic is fun, but symbols cannot be used. If you bring up the logic key that I gave you that shows you a bunch of the conditional statements, conjunctions, disjunctions, biconditionals, one of the things under conjunction, the and, is the but here. So logic is fun, but symbols cannot be used, can be translated. I'm going to do it over here, right? Logic is fun, that's Q, but symbols cannot be used, right? So Q and not R, right? That's ultimately what's happening here. It's auto capitalizing Q, but Q and not R. Logic is fun, but symbols cannot be used. Both of those things need to be true, right, for that statement to be true. Both Q and not R would have to be true for it to be true as a whole, because the conjunction means both are true. Number two, logic is not easy unless symbols can be used. Again, if you look at our logic key that I gave you, it's on Canvas. The unless shows up under the conditional, under the if-then. So anytime you see an unless in the middle of a sentence like this, what comes after the unless gets negated. So symbols can be used, gets negated. So we get not are, right? More specifically, if not are, then we just drop down what comes before the unless. Logic is not easy, right? So that's not P. We're negating P here, not easy. So if you have logic is not easy unless symbols can be used, that's translated into if symbols cannot be used, then logic is not easy. Okay? So again, look at the logic of the unless. What we're saying is that logic isn't easy, right, unless symbols can be used. The only way that logic is not easy, the only way it's not easy is if symbols cannot be used. Or to say it differently, if I can use symbols, right, if I'm able to use symbols, then logic would be easy. If I can't use symbols, then logic is not easy, right? So if symbols cannot be used, then logic is not easy. It's only easy, right, if symbols can be used. Number three, logic is fun only if symbols can be used. The only if means that we just drop this sentence right down, right? We say logic is fun, Q, if, right? If logic is fun, then symbols can be used, right? Logic is fun only if symbols can be used, which means if logic is fun, then symbols can be used. Logic being fun is sufficient to know that symbols are being used here, right? Number four, logic is easy and logic is fun if symbols can be used. This is tricky, right? It's going to be complex. Logic is easy, P, there's an and, right? Logic, and, but now it's a complicated sentence. It's an if-then sentence. So the way it works is you're going to put parentheses. Logic is easy and logic is fun if symbols can be used. It's not an only if. That's just an if there. So what comes after the if is symbols can be used, right? What comes before the if, in this case, it'll be the conjunction, or excuse me, the consequent, which is logic is fun. That's Q. You end up with logic is easy, P, and logic is fun if symbols can be used, which is translated, if symbols can be used, then logic is fun, right? So logic is easy, and if symbols can be used, then logic is also fun. So it gets symbolized this way. Now, the parentheses are helpful because it's taking that conditional and separating it from the conjunction a little bit, right? Number 5, logic is not fun if symbols cannot be used. This is not an only if. The if at the middle like this means what comes after the if is the antecedent, what comes before the if is the consequent. So if symbols cannot be used, which is not are, if, right, symbols cannot be used, then logic is not fun. If symbols cannot be used, then logic is not fun. I'll do one more here to maybe help. Symbols can be used, or it is not the case that logic is easy, right? Okay, symbols can be used, are, or, remember the V is the or here, the disjunction. Symbols can be used, or it is not the case that logic is easy. We negate P here. It is not the case, means we negate, right? And the or is in the middle. Number 7, logic is fun if and only if it is easy. So logic is fun if and only if logic is easy, P. If and only if goes both directions there. So hopefully this is helpful as we take language and we turn it into symbols. I'm going to scroll down. We'll do the opposite. But here we have symbols, and they want you to turn it into English using the same key. So remember, P is logic is easy. So this is easy. We have P over here, P and not R. The easier way to do it is to say logic is easy, but, right, symbols cannot be used. Or logic is easy and symbols cannot be used. Logic is easy and symbols cannot be used. The conjunction there works pretty easily. The next one, number 2 up here, anytime you have a negation outside of the parentheses, you start it in English with, it is not the case, right, that, and then we just do the conjunction. Logic is fun and symbols can be used. It is not the case that logic is, that logic is easy. That's P, right? P is logic is easy. It is not the case that logic is easy and symbols can be used, right? Or the next one, there's also a negation outside. It is not the case that logic is fun or symbols cannot be used. Excuse me, symbols can be used. That's just regular R. So we have here, right, it is not the case. If and only if, number 4, right? We got up here. Q is logic is easy. Logic is easy if and only if symbols cannot be used because it's negated, right? You can see the negation here, cannot be used. I'll do one more, number 5 over here. P is logic is easy. And, right, the and here, and if symbols cannot be used, then logic is fun. If symbols cannot be used, then logic is fun. So I hope this helps take symbols and turning into language. So we can go both ways, right? Here we took language, turned it into symbols. Over here we took symbols, turned it back into language. So now when we start to create truth trees, right, we're going to start taking our symbols and making truth trees out of them. You're going to need to know, right, when do I put a T under symbols? When do I put an F? When are the symbols true? When are they false, right, in the truth trees? And this practice over here on the left is going to help us. So they're telling us for these exercises, P is true, Q is false, R is true, S is false. So that's going to help us answer. So given that that's our key, Q, receive a capital T true or a capital F false, right? P is true, Q is false. Would there be a true or a false underneath? So think about that. You might want to pause me. In this case, it would be true because it's an or, it's a disjunction. In an or statement, only one of the two needs to be true, right? So only P or Q must be true. In this case, P is true, Q is false. One is true, which meets the disjunctive criteria. One has to be true. So we would say that's true. That's what we would put underneath it on the truth tree. Number 2, Q or S. Q is false, S is false. In an or claim, one must be true. In this case, both Q and S are false. So in the truth tree, that would receive a false underneath it, right? So that would be false. If both Q and S are false, it doesn't meet the criteria. All right. Number 3, P and Q or not Q, okay? P is true, right? So we got that. And we need one of these to be true, right? So P is true. Since it's an and, the primary relationship is the conjunction here outside the parentheses. That's the primary relationship. Then we need one of these other two to be true. And since it's a conjunction, both sides have to have at least a truth value to it. So P is true and not Q is true, right? Q is false, which means not Q is true. So we got P true. We've not Q true. So we've got truth on both sides of the conjunction, which is what we need. So we're going to get a truth there. That's true. Number 4, P and Q or R and S. Okay? The or is the major relationship. It's a disjunctive argument, right? That's the major one. One of these two have to be true on one side or the other, because remember, one has to be true and both can be. So P and Q, that is false because P is true, but Q is false up here. See? P is true, Q is false. P and Q needs both of them to be true, right? P and Q would need both of them to be true to receive a true underneath. P and Q is false, or R and S. R is true, but S is false. R and S is false. P and Q is false. So we have a false on both sides of the or. But remember, the or demands that you have at least one side have a truth, right? We have false, false, which makes the disjunctive argument false, right? That's a false. So the next one is very similar. P and R. So P is true and R is true. So this side is true, right? Or Q and S. Q is false, S is false. So P and R is true, Q and S is false, but since it's a disjunctive argument, it's an or, only one side needs to be true. Since the P and R side is true, the Q and S side is false, the whole thing together gets a true. Six, if P, then if S, then R. P is true, right? S is false, which means this conditional inside is true. Remember, anything can follow a false antecedent. So if S is false, then the inside is true, which means we have a true antecedent, we have a true consequent, right? So that's absolutely going to be true. Let's skip down to number 10. It is not the case R and S. So R is true, S is false. So R and S is false. But if we're negating it, we negate something that's false, which makes it true. So this is sort of how we're going to know what we put underneath the truth trees, right? This is practice for when we get there. So now we're going to move to doing some truth tree work. I hope this helps, right? So remember, the goal of truth trees, this cannot be lost on you. The goal of truth trees is to take symbols from an argument, line them up, and then figure out whether the argument's valid or invalid. Okay? So that's what we're going to do. So we're going to start with something easy. Okay? So you see the argument right here. Okay? Premise 1, if not P, then not Q. Premise 2, Q. Conclusion, P. Okay? Now, the way you set up a truth tree is right down here. You line it up across horizontally like this, and you put your individual letters first. So you have P and you have Q, and you have not P and you have not Q, right? All of those exist up here. And then you've got the conditional, if not P, then not Q. Okay? So we've got everything that we need here, right? So what you need to know when you set up the truth tree is, what are the premises? What is the conclusion? Okay? So the number 5 is a premise, right? Premise 1 is 5 here, where you can see the cursor. Premise 2 is number 2, the Q, that's premise 2. The conclusion is 1, P. Okay? The other two are not premises or conclusions, they're just here to help us. So number 5 is a premise, number 2 is a premise, column 1 is the conclusion. So here's how truth trees work. I cannot stress this enough. You have to listen to this, right? An argument is invalid if any of the columns, any of the rows, has all true premises and a false conclusion. Okay? An argument is invalid if any of the rows has all true premises and a false conclusion. If that is not the case, the argument is valid. That's how you read a truth tree. When you see all these T's and F's down here where the cursor is, when you see all these T's and F's, all they mean is if there's one of these right here, one of these rows that has all true premises and a false conclusion, then the argument is invalid. If that doesn't occur in the truth tree at all, then we say the argument is valid. We know it's in the right form. Okay, so let's go through it. The way I want you to do it is if you've got two letters like P and Q, so there's two primary letters and their negation, that means your truth tree will have 4 rows. Okay, so you see 4 rows, 1, 2, 3, 4, right? So if you have 2 primary letters, you're going to have 4 rows. If you have 3 primary letters, like let's say there was an R in this truth tree, so there's 3 primary letters, then you would have 8 rows. It doubles for every letter, so you'd have 8 rows going down. Okay? If we added a 4th letter, like T in the argument, let's say there were 4 primary letters, then you would have 16 rows running down. So it's exponential, 4 to 8 to 16. The most you'll ever have to do in this class is 16 rows, right? Most of the time it'll be 4 or 8. The way that you want to do it, the way you want to structure it, you want to lay it out across the top first. So you see your argument up here. You lay everything out across the top the way they've done here. And then you know for P, what are my options? True, true, false, false. If there's 4 columns, you go true, true, false, false. The very next column, you alternate true, false, okay? And then for the rest of it, you have to work it out. So for your primary letters, for those first 2 columns, if there are 3 letters, it would be your first 3 columns. You write in the T's and F's, right? With a 4 column, you go true, true, false, false. With a Q, you go true, false, true, false. And then you start working your way through. You'll see that when we have 8 columns, like 8 rows down, you would go 4 trues and 4 false for row 1. Okay, 4 trues and 4 false. Then you would go 2 trues and 2 trues, 2 falses, 2 trues, 2 falses on 2. 3, if we had a 3rd letter, it would alternate true, false, true, false, true, false. Okay. Once those 3 letters are set up, you can then do your truth tree. But for now, we've got 4. So the first column is going to be true, true, false, false. The second column is going to be true, false, true, false. Okay. So now, how do we do it? Well, we've got true, true, false, false, true, false, true, false. We start there. We go to not P, row 1. If P is true, not P is false. Easy, right? We move over. If Q is true, not Q is false. Easy. What about if not P, then not Q? Well, not P is false. Not P is the antecedent. If you have a false antecedent in a conditional, okay, if you have a false antecedent in a conditional, it's automatically true. Boom, you're done. Done with row 1. Row 2. If P is true, we know that not P is false, right? So P is true, not P is false. If Q is false, we know that not Q is true. What about the conditional? Well, we know that not P is false. Not P is the antecedent. A false antecedent means true conditional. Boom, we're done, right? We move down here. If P is false, we know that not P is true. If Q is true, we know that not Q is false. Okay? What about the conditional? All right, well, not P is true. Not Q is false. If you have a true antecedent and a false consequent, then you know you have a false conditional. True antecedent, false consequent, you know you put a false there, okay? Last column, P false, Q false, which means not P is true, not Q is true, right? The opposite. Well, then what about the conditional? Well, not P is true, not Q is true. If both sides of conditional true, then we get a true conditional below. The whole truth tree is done. Now we need to know, do any of these have all true premises and a false conclusion? Okay, so let's look. We know that column 5 is premise 1, true. Okay, we're on the right track. Premise 2 is Q, true. If the conclusion's false, we know it's invalid, but the conclusion is P and the conclusion is true. So we had all true premises and a true conclusion. That's fine. We're good. We're still good. We got to go to the next row. True premise, right? Premise 2, false. The moment you have a false premise, you know you can move on. Because the only way it's invalid is if you have all true premises and a false conclusion. That's the only way this can be invalid. So we know we have a true premise here, but once we have a false premise, we can move to the next row. False premise. So we know that this row is fine because the only way it can be invalid is if you have all true premises and a false conclusion. Once you get a false premise, that criteria can't be met. You move to the next one. We have a true premise 1. We have a false premise 2. So we know we have a false premise. All the rows are safe. This is a valid argument. It is deductively in the right form. And we know that because of the truth tree. We absolutely know this is deductively in the right form. And that's the way truth trees will work. I'm going to come back with another video doing some more complicated truth trees. And so hopefully that will help. But for now, I'm hoping this gives you some handholds. And I will look forward to seeing you online.